Welcome back. In today's video, we are going to be looking at the substitution and elimination of alcohols. If you remember from first semester organic chemistry, substitution and elimination both require your molecule to have a leaving group. However, OH of an alcohol is a bad leaving group. And so we must convert OH to a good leaving group first before we can do a substitution or elimination reaction. There are multiple methods of doing this, but one method is to use an acid to convert your alcohol into a water leaving group. If you use an acid with a non-nucleophilic base, like sulfuric acid, H2SO4, or nitric acid, HNO3, these reagents will do elimination. In this example, we have a secondary alcohol. This alcohol is secondary because the OH is connected to a carbon that's connected to two other carbons, and so that is a secondary alcohol. If we treat a secondary alcohol with sulfuric acid, the first thing that's going to happen is this alcohol gets protonated. And so some electrons on that OH are going to be donated to the proton on sulfuric acid, and then the electrons in the bond are going to go to the conjugate base here. And that's going to give you a protonated alcohol. So now that oxygen has a positive charge, and the bisulfate ion, HSO4 minus. Now what we have done is converted OH here into water. Water is an excellent leaving group because when it leaves, it's a neutral molecule and not charged. And so water can leave. These electrons in that bond are going to go up to oxygen, and you form this secondary carbocation plus water. Remember that carbocations are prone to rearrangement, and so you've got to be on the lookout for that. This carbocation has a hydrogen on a tertiary carbon right next to it, and so it can very easily rearrange and do a hydride shift to form a tertiary carbocation. That tertiary carbocation can then do elimination. Water can come in and protonate any hydrogen, deprotonate any hydrogen that's connected to a beta carbon, so the carbon right next to that that carbocation. And so this oxygen is going to give some electrons to that H, and those electrons are going to come and form a double bond. Like so. Now I chose to remove this proton here to get that product. There are three other carbons that are connected to that carbocation. This hydrogen here would give me the identical product, so I'm not going to worry about drawing the mechanism for that. But this carbon also has some hydrogens, and a water could come in and deprotonate that to give this product. So you likely get a mixture of these two alkenes in this reaction. However, this product is the major product because it is the most substituted alkene. So this alkene has 1, 2, 3 alkyl groups coming off of it. This alkene has 1, 2 groups. The more substituted the alkene, the more stable it is. And so the major product is going to be the most substituted alkene. We just saw that if you treat an alcohol with an acid that has a non-nucleophilic conjugate base, that we can do elimination. If, on the other hand, we treat an alcohol with an acid that has a nucleophilic conjugate base, so these are things like HX, where X is equal to a halide, or HCN, like hydrocyanic acid. These are acids that have a nucleophilic conjugate base, and so these are going to do substitution. And so if we look at this reaction here, we're using HCl as an example. And again, the first thing that happens is we have to convert that alcohol into a good leaving group. And so that alcohol is going to donate some electrons to that hydrogen and kick off that Cl to give you a protonated alcohol where oxygen has a positive charge and a Cl minus ion. Now, since this is a secondary alcohol, this can undergo an SN1 type reaction. And so this alcohol is going to leave, the water is going to leave. Alcohols don't leave, but water is a good leaving group, and so it can leave, just like it did before, and form a secondary carbocation plus water. Again, carbocations are prone to rearrangement. This carbocation had a hydrogen on a tertiary carbon right next to it. And so this can undergo a 1,2 hydride shift to get to a tertiary carbocation. When we used a acid with a non-nucleophilic conjugate base, there wasn't a nucleophile in solution, and so the best thing that could happen was to do an elimination. But HCl chloride is a pretty good nucleophile, and we just formed a chloride in the first step of this reaction. And so now that chloride has some electrons that it can donate to that carbocation, and we're going to form a tertiary alkyl halide. In this reaction, probably your halide could attack this secondary carbocation before that rearrangement takes place, but the major product in this reaction is going to be the tertiary alkyl halide formed here. In these two examples, we looked at a secondary alcohol, and so those can form secondary carbocations. Likewise, a tertiary alcohol could form a tertiary carbocation, and both of those carbocations are somewhat stable, and so they readily undergo SN1 and E1 type mechanisms. Primary alcohols are a little bit different. Instead of going through an SN1 or an E1 type mechanisms that we saw with the secondary alcohol, they're going to go through an E2 or SN2 type mechanisms that don't involve carbocations, because primary carbocations are not stable and aren't going to readily form. A second method of converting alcohols into good leaving groups is to convert them into a sulfonate ester. And so if we look at an alcohol as an ROH, in a sulfonate ester, that H is going to be replaced by a sulfur which is connected to 2 oxygens, doubly bound, and some R group. Now you might be thinking that sulfur has far too many bonds around it. If you counted the electrons around it, there's 12 electrons, and that's a lot. But remember that sulfur is in the 3rd row of the periodic table, and so it's allowed to expand its octet. And so this is a perfectly reasonable Lewis structure. In organic synthesis, there are 3 sulfonate esters that occur a lot, and so I thought we would look at those structures. The first one is a mesylate. You will often see that abbreviated as OMS. And a mesylate is a sulfonate ester in which this R group is a methyl group. Another common one is a tosylate. That is often abbreviated OTS. And a tosylate, the R group is a benzene ring with a methyl group in the 4 position on that benzene ring. And the last one that's fairly common is a triflate, which is often abbreviated OTF. And then a triflate, the R group is a trifluoromethyl substituent. Of these 3, the triflate is probably the best leaving group. And it's probably on the order of, say, an iodine or an iodide as a leaving group. Mesylate and tosylate are slightly worse than a triflate, and they're probably on the order of, say, a bromine or a Cl minus, a bromide or a Cl chloride leaving group. If we look at how these sulfonate esters are formed, for the tosylate and the mesylate, they're going to start with a chloride. If we're looking at the tosylate, it's going to start with a tosyl chloride, and I see that my tosyl chloride is missing a methyl group, so I'm going to go ahead and toss that in there. And in this case, I'm reacting with a secondary alcohol, and in the first step, the electrons on my oxygen of the alcohol are going to come in and attack the sulfur. And that's going to give sulfur too many electrons. And so the electrons in one of these oxygen sulfur double bonds is going to kick up and go to that oxygen. And that's going to give us an intermediate like so. There's a lot to draw here. And in a second step, the electrons on oxygen are going to kick back down to sulfur, which kicks this chloride off. To give this intermediate here. And in the last step of this synthesis, I dropped a methyl group. In the last step of this synthesis, pyridine, this molecule here, is a good organic base, and so it's going to come in and deprotonate this oxygen to give the final product. here, which most organic chemists would abbreviate as OTS to indicate that this is a tosylate. The mechanism for forming a triflate from an alcohol is very similar to that of forming a tosylate or a mesylate, with the exception that the starting material is slightly different. The triflic chloride is not a readily available molecule, and so instead we often start with the triflic anhydride. And so in the first step, just like before, the alcohol is going to donate electrons to one of the sulfurs. It doesn't matter which one here, they're the same. And that's going to kick up some electrons on that oxygen. And that's going to give you an intermediate that looks like this. Rather than drawing out the other side, I'm just going to label this OTF. And so this group, or this portion of this molecule, is an OTF group. And after that, the oxygen can kick some electrons down. And remember, triflate is a good leaving group. And so that OTF is just going to be kicked off. And that's going to give you this molecule here. And again, this portion of this molecule can be abbreviated as OTF, and so most organic chemists would draw this like this. And then remember, pyridine is an organic base. Looks like this. And this nitrogen has a lone pair that it can use to deprotonate there, which is going to give you the final product here. It's worth noting that when you convert an alcohol into a leaving group, that into a triflate or a tosylate or any other sulfonate ester, that the oxygen here is the same oxygen that was in this alcohol up here. And so whatever the configuration of your alcohol was, it's going to be the same in your final product. Like halides, sulfonates are good leaving groups, and so sulfonate esters are going to react very similarly to alkyl halides. So in this example, we have the tosylate that we formed a couple of slides ago, and it's a secondary tosylate. And so if we react that with sodium cyanide, which is going to break up into a sodium ion and a cyanide ion. Cyanide is a weak base, but it's a pretty good nucleophile. And so it's going to attack this tosylate and kick that OTS group off in an SN2 type reaction. And remember, SN2 occurs with inversion of configuration. And so if that tosylate was coming out of the page at us, this cyanide is going to be going back into the page, like so. So secondary tosylates with relatively weak bases but good nucleophiles can undergo SN2 type chemistry. On the other hand, if we treat this tosylate with potassium tert butoxide, looks like this. So it's an alkoxide that splits up, and tert butoxide is a very bulky base, and so it's not a good nucleophile. So rather than doing substitution, it's going to do elimination. This reaction has, or this compound has a couple of hydrogens that could be deprotonated. So if we pick that one, it's going to kick that off, or pull that proton. Those electrons go down and then kick this tosylate up, which gives you this product. That methyl group's configuration wasn't changed, and so it's still going back into the page. There's also a different hydrogen that could be plucked off, and so I'm going to redraw this molecule so it's a little easier to see. So in the last example, we deprotonated this hydrogen. However, this hydrogen could also be deprotonated. Which would give you this product. This methyl group here means that this hydrogen is more accessible than that hydrogen, and so I would expect the major product to be the proton that's easiest to remove, and so likely this is the major product, although I expect this minor product will also be observed. At the beginning of this video, we saw that you could convert an alcohol into a chloride using acid. But that often goes through a carbocation, and so it can get messy. An alternative to using acid is to use a reagent known as thionyl chloride, or SOCl2. And in this reaction, or this alcohol can donate electrons to sulfur, just like we were forming a sulfonate ester, and that sulfur is going to kick some electrons up towards oxygen, like this. It's going to give you an intermediate. It looks like this. These electrons on oxygen are going to kick back down and kick that chloride off, like so. I left this methyl group off. I'm putting it back in. To give this intermediate. Where this oxygen is positively charged. That methyl group is still there. Now remember, pyridine was a good base, and so I'm just going to use B to indicate base. But the electrons on that B are going to come in and kick down, pull that proton off. For this intermediate. Now, if we go back a couple of steps, we lost a chloride, and I didn't draw that in, but I'm going to draw it in now because we need it. this chloride is going to come in and attack that carbon with oxygen in an SN2 fashion, which is going to kick these electrons up to sulfur, and at the same time that Cl is going to fall off. And so you wind up with this molecule here. And remember, the Cl attacked in an SN2 fashion, which does inversion of configuration. And so that's the organic product that you get. And in the same step, you lose SO2, which is a gas, and Cl minus here. And so this gives you a way to cleanly convert an alcohol into a chloride, but it's going to give you inversion of configuration. We've seen a couple of ways to convert an alcohol to a chloride. One was HCl, and that was not very clean. It went through a carbocation. We just saw that you could use thionyl chloride to do it cleanly and get to a inverted configuration for a chloride. HBr will also convert an alcohol into a bromide, but again, that's going through a carbocation. And so if I wanted to do it more cleanly, you would choose to use phosphorus tribromide, or PBr3, to do that. In this reaction, PBr3 is going to react as a electrophile, and I'm going to redraw that so we can see the bonds here. And oxygen has some lone pairs. It's going to donate electrons to that phosphorus, and that Br is going to get kicked off, very similar to an SN2 type reaction, but this time it's occurring at a phosphorus atom instead of a carbon atom. And that's going to give us an intermediate. It looks like this. And then again, we've got pyridine in this reaction. Pyridine is a good base. And so I'm going to use my base to pluck off this proton. And this OPBr2 is a good leaving group. And so Br minus is going to come in and attack this carbon and kick off that OPBr2 in an SN2 type reaction. So remember, SN2 is inversion. And so if that OPBr2 was going out of the page, Br is going back into the page, and I also get this weird inorganic leaving group. So again, if my alcohol was coming out of the page, my Br is going to be going back into the page. So this is going to give you inversion of configuration when you convert your alcohol into a leaving group. So we've seen a couple of different ways to convert alcohols into leaving groups, and so I thought we should discuss why you might choose one over the other. And the key to that decision really is the stereochemistry of these reactions. So if we look at the starting alcohol here, this is a secondary alcohol. It's chiral and enantiopure. And so if we were to take that alcohol and treat it with phosphorus tribromide, phosphorus tribromide converts an alcohol to a bromide or an alkyl bromide, but it goes through inversion of configuration. And so since that alcohol was coming out of the page at us, the bromide is going to be going back into the page. If we then treat that with something like this reagent, which is going to split up into sodium plus and SET. Remember, that's a sulfur with an ethyl group attached to it, with a minus charge, and that sodium had a plus charge. This is a reasonable nucleophile. This is going to undergo an SN2 type reaction, and so this pair of electrons is going to get donated there and kick that bromide up, which is SN2, and so that is doing inversion of configuration again. Since that Br was going back into the page, this sulfur is going to be coming out of the page. On the other hand, if we convert that alcohol into a tosylate using tosyl chloride, remember that the oxygen in the alcohol is the same oxygen that's in the tosylate. And so the configuration of the alcohol is identical to that of the tosylate. And so I'm just going to convert that alcohol into a tosylate and leave that oxygen coming out of the page. Then this reagent here is going to do an SN2 type reaction on this tosylate. But this time, since the tosylate is going out of the page, the sulfur is going to be going back into the page. So substituting an alcohol going through a tosylate is going to give you inversion of configuration. However, if we want to do substitution using something like PBr3 or thionyl chloride, would also do the same thing. And I want to get to this sulfur containing product. This is going to give you net retention of configuration because the configuration was inverted twice. Once when we converted it to the alkyl bromide, and a second time when we treated it with sodium ethyl sulfide to get to this final product. The last thing I want to talk about is a way to do E2 eliminations with alcohols. At the very beginning of this video, we saw that if you treated an alcohol with something like H2SO4, you could do an E1 elimination. But E1 eliminations go through carbocations, and those are prone to rearrangements that can cause problems. And so it might be advantageous to be able to do an E2 elimination. And one way you can do that is using phosphoryl chloride or POCL, POCl3. If you treat an alcohol with POCL, the oxygen can donate some electrons to phosphorus, which is going to kick electrons up. And give you an intermediate. That looks like this. These electrons on this oxygen can then be kicked down, which is going to kick off a chloride. To give this intermediate. And then remember that pyridine is a good base. And so the first equivalence of pyridine is going to be to deprotonate this oxygen. To give this neutral intermediate. And then the second equivalent of pyridine is going to be used to do the elimination. And so I'm going to draw in this hydrogen here. And a second equivalent of pyridine, I'm just going to use the same one though, comes in and deprotonates there. Those electrons get kicked up, and that oxygen leaves to give you this final organic product, and your leaving group was this molecule here. Now I've shown the major product of this reaction because it forms the most substituted alkene. There's also another hydrogen here that could be deprotonated. And that product looks like this. Again, the most substituted alkene is the major product in this elimination, but you probably will observe some of this terminal alkene shown here. That's going to wrap up today's video.